Today we'll continue our discussion of log linear models. One of the first things that I want to discuss is this word, hierarchical. So these log linear models are often called, in some of the literature, hierarchical models. And there's a reason for that. And let's talk about what that reason is for a moment. So think about a two-way table. Our saturated model looks like this. We have a global term. We have a term for the x variable, a term for the y variable. So this is number of outcomes minus one of each of these, or number of outcomes minus one sort of degrees of freedom with maybe we have all of them and we have constraints of some kind that eliminate the redundancy. And then we have the joint term. So one thing that you should notice about a model like this is that it's hierarchical in the sense that whenever I have a term in the model, like this term, I have all sort of smaller terms. Right? If I have an xy, I have x, I have y, and if I want to think about this as a set, I can think about that as like the empty set. Right? So for all of the factors that appear, the factor xy appears. Also, the factor x, y, and nothing appears. If I had a factor for x, y, z, like a three-way interaction, I would also have the factor xy, xz, yz, x, y, z, and the empty set all appearing. So a lambda for each of these things. Okay, so it's hierarchical and set in that sense. And this is connected to the idea of what's called a simplicial complex in mathematics. So a simplex is just a set of points. So say I have 2 points and I give them a name like x and y. Simplex is the set that contains all of them. And implicitly it sort of contains its faces. So if I have this simplex x, y, z, it contains this sort of set of x, y, and z, and I can think of it also as containing x, y, and y, z, and x, z, and x, y, z, and the empty set. Okay, so that's kind of the picture of what's happening. And a hierarchical model will be a simplicial complex, which is a bunch of these simplices glued together at intersections, like this. And we wanted to include all of the faces of each of these simplices, including the face at which they're joined. Statistically, so hierarchical models correspond to simplicial complexes. Statistically, what's going on? Why do we need these lower order terms? By which I mean without these contained terms that come from the smaller things. The significance and interpretation of the higher order terms would be different. It's different, or another way of saying is that it depends on how it's coded. So, and to see this, it's pretty easy to think about. I mean, so if I wrote this model down and I included this interaction term and I forgot to include the term that controls the marginal of x and the marginal of y, when I fit the model, the interaction term would kind of have to absorb that information. So this would have to change in order to make the marginals match. And so the information about the interaction gets confused by having to include the information about the lower order stuff. So for the interaction to really represent an interaction, we have to include all of the lower order terms, or all of the smaller faces of the simplex. Okay. So if we did that, if we said log uij is lambda plus lambda ix plus lambda ij xy, so we're missing the lambda that corresponds to y and it controls that marginal. We've sort of interlinked the interaction term with y, and this is related to the sort of constraints that we've made. In other words, we've forced that log uij equals lambda for every column j. And usually that's not what we want to do unless we have some specific idea of our model that makes sense. I also say that when we do include the interaction terms, the analysis of the model should probably be focused on those interaction terms. And at the same time, the effects, the estimates of the main effects, so we've seen that when we include interaction terms, the main effects will change. Because some of that dependence gets absorbed into the interaction term anyway. And so the estimates of the main effect will depend to some extent on how the higher order terms have been parameterized and their interpretation. So when we're including the interactions, the story is that we should focus on that analysis. We're far enough along now, and you're digging into your projects, that I think you may begin to run into some of the problems where the theory that we've set up so far doesn't always match exactly to the situation. And one of those things that can happen is zeros and sparsities. I'll spend a few minutes talking about that. So in some studies, so suppose we have a sample size of 30 subjects, and maybe we're measuring something in a classroom, and we start measuring more and more characteristics. Of course, there are ways of explicitly dealing with this situation, which some of you are looking at, but let's just think about it with the techniques we have so far. So we start measuring more characteristics of these because we don't cover everything. And so we start with like a 2x2 table, and then we get a 2x2x2 table as we ask more questions or characteristics, yes, no characteristics. And at some point, the next one, 2x2x2x2, we have 32 cells, 2 to the 5th. And so we have more cells than we have subjects. And so certainly at this case, by the pigeonhole principle, but also possibly in the smaller cases, we're going to have zeros. And so this kind of zero is what's called a sampling zero. The idea being it was at least possible that every cell in the table could have had a value in it, and that we just didn't happen to observe it. Alternatively, we might be forced to have zeros for sort of a theoretical reason. So for example, we could have a cancer study where we have cancer type, and we have gender, male, female, and we have prostate, ovarian, and other. And we make a table. And we have a number here, and we have a number here, and we have a number here and here. But men can't get ovarian cancer because they don't have ovaries, and similarly for women. Right? So these zeros would be structural zeros. That's the name for them, whereas that's a sampling zero. And so this is a zero which somehow the laws of our experiment have prevented it from being even possible that one of these things could occur. Okay? we want to discuss a little bit what we should do in each of these situations. So in this one, in some sense, what's going on is that you have to use a different model, right? Because your model that assumes that all these things could be non-zero is just fundamentally wrong, and we have to think about how to rephrase the model to do that. In this one, we have a little bit more flexibility because it's not that the model is wrong, it's just that we don't have enough data, so we want to somehow smooth it. So let's focus on that first case, sampling zeros for now. So in sampling 0, we have some nij is equal to 0 in the sample, but we believe that the true probability pi ij is positive. That is, if we had a large enough sample, we would finally observe something in that case, if n were large enough. Whereas in this one, we believe that pi ij really is just 0. No matter how large I make n, nij will always be 0. A particular way where these structural zeros can appear is something called incomplete classification. So we had this example a couple of weeks ago about presidential approval ratings, where we took a survey of a bunch of people, asked them what they thought of the president, and then we waited 2 years and took another survey and asked them what they thought. And there was something very unrealistic about that example, which is that we managed to find everyone again. Right? So everyone we asked the first time, we asked the second time. It was exactly the same people both times. And if you really did the survey with 1,600 people or 10,000 people, that wouldn't happen. Right? You wouldn't be able to find everyone. So a more realistic version of that would be something like we have time 1. We're surveying something, yes, no, not sampled. Right? People that we didn't ask at time 1, but we might have asked at time 2. We have a time 2. Yes, no, not sampled. And we have some information here, which is our original table that we know how to do the analysis on. And then we get these people here, which were classified at time 2. Maybe we only found 50 of the people of the 1,600, and we threw in another 50 that, in order to fill out our survey. And these are people who were classified at time 1. And then this is just 0 because there's nobody that we didn't sample them either time. There's no point in putting them in the table. Right? So there are techniques for dealing with that, if that's something that shows up. So this is in the past, when I've taught this class, this has been something that showed up in people's projects. So let me give you a couple of references if this is something that shows up for yours. Chen Feinberg, 1974. Partial cross-classification. So basically, we use the same kind of technique we did for the 2x2 version, but with some adjustment for the fact that we have this missing data. And there's another one by Haber, Chen, Williamson, 1991, analysis of repeated categorical responses from fully and full and partial cross-classification. In the last time that I taught this class, the example here was in people who were studying forest ecology, and they were looking at trees. And they looked at a stand of trees separated by 5 years or something. And so some of the trees had not started growing yet at time 1, and so they were in the time 2 sample, not in the time 1 sample. Some of the trees had died or been cut down, and so they disappeared for that reason. So in any real data, that's going to happen. Okay, so then let me talk about a couple of things that happen with sampling zeros that I'm erasing right now. And this is sort of one of those ironic things, right? So if you write a pretty good survey, you have only so many subjects and you ask them a lot of questions, it's generally the case that this happens, right? You get some configurations of answers that never occur. And in some sense, being good about your data, being good about using all the people that you have and asking them lots of questions will sort of make this inevitable. So what can happen? Two bad things can happen, at least. One, when we try to fit a maximum likelihood estimate, it might exist, but it's biased. So another thing that's happening here is that we're saying the sampling distribution of the fit statistics, like the chi-squared, poorly approximated. So, not only is our maximum likelihood estimate biased, but even our estimate of fit is not very good, because when there are a lot of zeros, as we know, our g-squared and Pearson statistics are not well approximated by chi-squared. And then the other thing that can happen is that the maximum likelihood estimate does not exist at all. And we'll see in a little bit that, unfortunately, your software does not always tell you this. It might spit out an answer anyway. But what's really happened is that it's gone off to infinity. So I should warn you that which of these cases we're in, so the existence of a maximum likelihood estimator in the presence of sampling zeros, is a subtle question. And it's actually a question that's actively being looked at right now in research. So in other words, take a data set and tell me, does the maximum likelihood estimate exist or not? Give me criteria for whether or not it exists. So this paper is being published in the last couple of years about that. So that's not that easy. And essentially what happens is it depends on the pattern of zeros and how that interacts with the pattern of interactions. So remember that in a log linear model, we can think about I have a bunch of variables, x, y, z, w. And my job in modeling is to decide which subsets of these I want to measure. So I'm sort of forced to measure all the marginals generally, right? And I have a global term that kind of handles the global total. And then I decide, maybe I want to look at the zy marginal. Maybe I want to look at the zwy marginal. Right? We have different notation. I'm writing it in circles right now, but usually we would write something like, that's the xz marginal, and here's the yzw marginal, right? So I have to decide which subtables I want to tabulate. Okay? And those correspond to the parameters, the lambdas. And you might see that, right, if I only choose to look at subtables that don't have zeros in them, then I'll probably be okay. And that's more or less true. If I look at subtables that do have zeros in them, I may or may not be okay. So that's kind of the idea. So let me give you a reference on that. There's one Erickson, Feinberg, Ronaldo. Sullivan 06. So this one, this paper treats this situation, and let me say what the conclusion of that one is. So that paper says that the non-existence of the MLE is equivalent to the margins of the observed contingency table lying on a facet of the marginal cone of the underlying hierarchical log linear model. So I don't expect you to understand exactly what that means, but the intuition is like, it's not so different from this case where we were thinking about just estimating a Bernoulli probability, or from a binomial distribution. The point is, like, as you get close to 0 or 1, everything goes haywire. So now we're in a much higher dimensional situation. You can kind of think about a fan or a polytope of stuff. And when we get close to one of the boundaries of that higher dimensional object, like it's a big cube, when we get close to a vertex or an edge or a face, things start to go haywire. That's the basic intuition. Okay? And let me give you an earlier result that is a positive result. This is Haberman, 1974. And this says that under Poisson multinomial, or product multinomial, sampling, the MLE exists for a model. I'm going to write A for a second, and data, let's call it U, if and only if there exists a vector Z in the kernel, the matrix A, such that U plus Z is strictly positive. So let's try to magnify that a little bit. See how that relates to some of the other things we've been discussing. So I called a matrix, this matrix A, last time, I drew 2 times ago, I talked about a matrix A which is related to the models. Anyone remember what that matrix represented? So to a log linear model, I can associate a matrix A, which helps me keep track of how many free parameters I have. Right? So for example, say I have 2 variables. And there are 8 possible outcomes. 3 variables, there are 8 possible outcomes. And a matrix A would represent all of the sufficient statistics that I read off from these outcomes, or equivalently all of the parameters that I include in my log linear model. So let's see if we can fill in a couple of rows. So suppose, let's say, okay, so for the independence model, if I don't impose my constraints, I'm going to get, or let's impose constraints. Let's say lambda 0 x, lambda 0 y, lambda 0 z. You remember what I fill in for those rows?
The top row is 1, 1, 1, 1, 0, 0, 0, 0.
1, 1, 0, 0, 0, 0. And that's just because at each of these things, x is equal to 0. Okay? And this is the parameter that's associated to x is equal to 0. For y equals 0, I want to look at when the second one is 0. So 0, 0. Sorry, that's the other way around. 1, 1, 0, 0, 1, 1, 0, 0. And for the last one, I want to look at when z is 0. So z is 0 here. It's not 0 here. It's 0, not 0, 0, not 0, 0, not 0. And then I would need an additional row if I want for my lambda. Let's put that in, which is just all ones. So something happened in my count. I have a global parameter. And then I have parameters for each of these things. So far, there are no interaction terms whatsoever. Let's add an interaction term, like lambda x, y, 0. X and y are both 0. So I only need one interaction term for that. And which of these would be 1 here? So 1, 1, the rest are 0, 0, 0, 0, 0. And you can see if I added more interaction terms, maybe if I added a yz, you get another row. Okay, so such a matrix like this, which keeps track of all of the things that I'm measuring, all of the marginals or co-occurrences that I'm measuring, or equivalently all of the parameters that I'm including, this is one of these matrices A. The kernel of A is the set of all vectors in this space, 8-dimensional vectors, which when I multiply the A by that, I get 0. Okay. What is the data doing here? So I can think about the data as just a vector of counts. So this is just another way of writing my contingency table. So if I have a 2 by 2 by 2 table, so like say x, this is x, or this is x, this is y, x, y, and this is z. Here is u 0, 0, 0, u 0, 1, 0, u 1, 0, 0, u 1, 1, 0, u 0, 0, 1, u 0, 1, 1, u 1, 0, 1, u 1, 1, 1. So these u's are just the counts of the that appear in the contingency table. Okay? I can write that u as a long vector, u 0, 0, 0, u 0, 0, 1, u 0, 1, 0, u 0, 1, 1, u 1, 0, 0, u 1, 0, 1, u 1, 1, 0, u 1, 1, 1. Right? This is just the numbers. These are the counts that I observed from my experiment. How many people had x equal to 0, y equal to 0, z equal to 0? That's this number. How many people had x equal to 0, y equal to 1, z equal to 0? That's this number. So on. Okay. So I take this vector of counts, I multiply it by this matrix A, and so what this theorem says is that if I can take my data and translate it by a z that's in the kernel of A, which means A is blind to that translation. Right? It's something that A can't see at all because it's 0 when I multiply A by it. If I can translate the data by that amount and get a positive vector, then the MLE exists. So another way of saying that is the MLE exists if and only if there is some real valued table U prime. So I started with U, which was my true table. I have a new table U prime, which I'm not requiring to be counts. They're allowed to be just real numbers. U prime with strictly positive entries. And from the point of view of A, from the point of view of my model, it doesn't matter which table I use. So what I've said in equivalent, essentially, is I'm saying, I take a model which has structural, I take an observation, I take a result, an experimental result which has structural zeros. If I can manipulate it by some vector z, which is in the kernel of A, so in other words, it doesn't change the sufficient statistics at all, into a new vector of sort of pseudo counts, which are all strictly positive, so they no longer have any sampling zeros in them, then it's okay. The maximum likelihood estimate will exist. That's what that theorem says. And the theorem I just erased is sort of a refinement of that. So let's look at some examples. So you might hope, as I suggested earlier on, that at the statistics, or the counts, the joint counts that we measure, will MLE exist. So you might hope that would be true. It's not quite enough, so it's not quite true. So suppose at least one of the counts is 0, but all of these things we measure, the quantity that I would get in each of these rows after I multiply the counts by this matrix, these are called the sufficient marginal counts, are all positive. Then the MLE exists if the model is decomposable, which I'll define in a second. So for example, this model, the conditional independence model, is such a model that's decomposable. In fact, the maximum likelihood estimate for the no three-way interaction model exists if only one cell is 0, but it might not if two cells are 0. So the MLE for xy, yz, xz exists if one cell is 0, might not for 2. So for example, let's do x, y, and z, the third dimension. So if I have 0, something, something, something over here, and I have something, 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 0, where the somethings are all non-negative, if I have a table that looks like that, then the maximum likelihood estimate does not exist. So I said it does if we have sufficient marginal counts. If the marginal counts, the things that we're measuring, the things that correspond to the parameters are all positive, and the model is decomposable. And let me tell you now what I mean by decomposable. So first, let me give you a couple of examples. So this model is decomposable, this model is decomposable, this model is not decomposable. So the definition is that we call a hierarchical model, or a simplicial complex, because that's the data that we're interested in right now. Doesn't matter how many states there are. Is reducible if reducible, say, into submodels gamma 1, gamma 2, gamma 1 S, gamma 2. If gamma is equal to, a hierarchical model of gamma is equal to the union of these two, and the intersection is a simplex on S. So, for example, let's do another example. XYZ, WYZ. So this model is decomposable because I can split it into two submodels, XYZ and WYZ. These two models have an intersection, which is YZ, and YZ is a simplex, is a saturated model. So we want the intersection of these two things to be saturated. So it's a bunch of pieces, simple pieces, all glued together along saturated models. You can think about it as, oh, sorry, that's reducible, so then decomposable. It's decomposable if it's reducible and the results are themselves decomposable or just simplices. Essentially, I can build this thing up as a tree. So a simple way of saying this is that a decomposable hierarchical model is a tree of maximal factors. Factor being one of these largest things, one of these boxes, the biggest interactions that occur. So if I look at all the biggest interactions that occur and I glue them all together, I get a tree. The vertices of this tree are these facets of the model, these largest interaction. And the edges are these separators, S, that split the pieces. So you won't see too many of these until you have a lot of variables. I know some of you have a lot of variables in your projects from what I've seen so far. So you maybe end up considering these. And you want to consider, if you can, decomposable models because they're easier to work with. One reason is that this is essentially the nice case where iteration isn't needed. In other words, where we can just write out generally the solution to the MLE. So if I have a vector of data with positive marginals, which was in other words, when I measure all my sufficient statistics, I get positive numbers. Then our estimate, our expected cell counts under the model, let's say this is a vector, an I, multi-index that indexes like 0, 1, 0, 0 or something if I have 4 variables. Okay. So this is equal to the product over all of the maximal factors the count restricted to that factor, the index restricted to that factor, divided by the product over all these separators in the edges of this tree, j of gamma being this tree of factors that we can build, mu restricted to the separator given the index I, this restricted to the separator. Okay. So you probably won't use that as a formula to compute it, but the software you use might use that formula. And this looks complicated, but it's just the generalization of what we do for the independence model. So independence model, we can express the entries in terms of just the marginals, right? Just the overall marginals for each variable. When we have this kind of tree structure, it's possible to express all of the expected things in terms of the marginals, and that's how you do it. Okay. So what happens when we do have counts that are 0 and we're not lucky such that one of these situations hold? It's not a decomposable model. We don't have positivity. What happens? So one thing that can happen is that we can get infinite estimates for MLE. And generally, your software is not going to output infinity. It'll output something else. So let's look at an example. So suppose we have a multinomial 2x2 table. This is a very degenerate example. We have an x and a y, have a 2x2 table, and everything is 0 except for x equals to 1, y equals 1. And we're going to encode x equals 1 as 1 and x equals 2 as 0. So our model is going to be log for multinomial, so I'm putting pi's here. And in that interpretation, lambda is the constant so that things sum to 1. X equals 1 plus lambda y equals 1 plus lambda 1, 1 xy. And then I should think about this having, indicator functions like dummy variables y equals 1. So the probability of the outcome 1, 1 is 1 over z x lambda 1x plus lambda 1y plus lambda 1, 1 xy. And if I work that out, I'll end up getting 1. And so lambda xy 1, 1 is going to get sent to infinity by when we try to estimate it. So sometimes not even infinite estimates exist. So for example, if I had the table 0, 0, n12, n22, and I wanted to estimate the log's odds, well, the odds ratio would be 0 times n22 divided by 0 times n12, so I have a 0 over 0. It's just an undefined number. Okay? So in our software, dealing with this stuff, sometimes it will automatically try to fix the situation, and sometimes it won't. Generally, it's not automatic. If you see extremely large parameter estimates, usually it won't output infinity, but if you see extremely large estimates, that's an indication that something is wrong. If you see ahead of time that there are zeros in your table, that could be an indication, although it may be not immediately obvious unless you ask it to tabulate, right? Like if you just enter the data rows, you might not see immediately that there are zeros in the table that you're asking it to look at. You might see odds ratios that are 0 or that are infinite. I bring this up now because, of course, so far in the class, most of the canned examples which we've given you in the notes and in the homework have been constructed to avoid this problem. But now that you're looking at your own data, it's no longer constructed to avoid this problem, and you will run into this problem. So your software might say, I'm not going to do this. It might not converge. It might just keep running. It might spit out warnings. What are the warning signs? One big thing is that the standard errors blow up. So you expect a small standard error, and you get a standard error that's like 10,000 or something, right? Some huge number. For something like an odds ratio, that's a sign that there was a failure to converge or that something went wrong. In SAS, you'll get warnings like negative of the Hessian is not positive semi-definite. Right, so it will say something like that, or convergence is questionable. Right, it will tell you that it's having trouble finding it. There's so especially, but even if you don't see anything, whenever you see the standard errors blow up, which happened, for example, in our alligator example, that's a sign that something like this has happened. So here's a numerical estimate, a numerical example. So we have x and y, 0, 5, 0, 16, and x and y, 6, 9, 5, 7, and this is z, is the variable of which subtable. So if I just do an x cross y subtable, or an x cross z, so these are marginal independence models, or marginal models. These are okay, right? There won't be any zeros in that. But the y by z table looks like yz, 0, 11, 21, 16. So that's has a 0 in it, and that suggests that, likely, when I run my log linear model and I try to estimate the coefficient lambda 1, 1, yz in, say, a no three-way interaction model or a homogeneous association model, this might be a problem. Okay, and lo and behold, if you run this in like SAS, this one I think is a problem, but also if you look at the saturated model, so it will take, for this one, it'll estimate it, it will happily estimate it, and it'll give you a standard error of 139,605. So if you ever see something like that, that's what's going on. There's a 0 probably somewhere in your table, or some other collinearity, and something is wrong, and you need to rethink your model so that you're not trying to estimate that coefficient. Interestingly, some analysis is still fine, even when we're in this type of situation. So for example, if I'm in a situation like this, like we just had, where these three are all positive, of course, when we try to compute a log odds, it'll be negative infinity. If your software is doing what it should, you might be able to ask for a confidence interval. If you ask for a confidence interval, this thing will be finite and okay. Perfectly fine. Okay, so we can get sort of partially good estimates. So our point estimate is nonsense. Our confidence interval is half nonsense, but our we still can get an upper bound that makes some sense, because we do have some data, right? And we're able to say something. Okay, so what do we do? Any suggestions? What should we do? In some sense, we've seen this before. What's the first thing that comes to mind? That's one of the solutions. Change the zeros. Right, so one of the things we can do is we can add a small amount to it. Two typical numbers to add is you might add 1/2. That's a common thing. And sometimes the software will automatically add some tiny number. Like it'll add 0.001, just so that things start converging. So if I added even 0.001 to this, it would be much cleaner. Right? It would give me some interval, which was huge here, but it wouldn't spit out infinity. The other thing we can do is we can merge cells. It's a little tricky to answer the question of whether merging cells is statistically reasonable, because we have this problem with zeros in it. But if we believe, for whatever reason, statistically or hypothetically, that merging the cells doesn't cause a problem, it doesn't change the inference that can be a good option. Of course, whenever we merge cells, we have to worry about Simpson's paradox. So those are the two of the basic approaches. Anyone think of another approach? Something else that we talked about in the model selection context can be used here. So the problem in some sense here, if this is a sampling zero, right? The problem is that our model is taking this zero too seriously. It's believing the data 100%. It has no common sense. Right? So how do we insert common sense into our model? So like if we believe that all these probabilities have got to be positive, for example, how do we push the result towards having positive probabilities?
Can we add all an extra term to represent?
It does involve adding an extra term. So implicitly, right, where did this estimate come from? This is a maximum likelihood estimate, right? It's a maximum likelihood estimate that uses as its input only this information. Remember, when I was talking about model selection, we saw that if we have prior beliefs about the data, we have prior beliefs about the model, right? We can have a prior on the parameters, and we can incorporate that information. Or we could use sort of the shortcut version of the prior, which is to penalize this, right? So we could sort of add another feature to it that mixes what we know about the data and some kind of prior information. Right? So we could do that by doing a full Bayesian. Right? Once I have a distribution over this theta, that's like saying, I don't believe this zero 100%. So we could use a full Bayesian approach, or we could use like a regularization approach. And regularization approach has been extremely successful in dealing with this situation where the sample size is much smaller than the number of cells. Right, so this is this like L1 regularization or lasso, whatever, right? So this strategy, which you can think of as being kind of a shortcut to the full Bayesian, has been very successful in dealing with this situation. And so what we do is we take our likelihood that would have as its maximizer would go off to infinity, and then we penalize it by some function of the parameters. And that will be enough to, right, because this is, if theta is going off to infinity, this penalty will go off to infinity. right? The size of theta will go off to infinity, and by adding this size as the penalty back in, we kind of balance it and we force this thing to not be allowed to go to infinity. So this sort of thing is kind of a well-founded way. You could think of it as always smoothing your parameter estimates back toward something uniform looking, or something simple. Okay, so that's one method which is perfectly good and works pretty well. Let's go zoom in a little bit on the adding constants idea. So this is more ad hoc, but it often works pretty well. We can add 1/2 to each cell, sort of quick and dirty, and we'll often get you to a simple a result. Even in a 2x2 table, this can cause a reduction in bias that's caused by this sort of problem. Of course, if our table is too big, in other words, I have many, many entries and n is too small, then all these 1/2s that I'm adding will swamp the data. Right? You can imagine a situation where the total value of all the 1/2s is a multiple of the sample size, in which case you'll destroy almost all of your signal. So this works best when that's not the case. And of course, it will weaken the effects that we see, and it will weaken the test statistics. And software, as I said, sometimes your software will add some number like 10 to the minus 10 to each cell. Right? If it's just in order to force it to converge, you have to look carefully at the answers that get spit out to see whether what it produces makes sense. What else can we do? So in both the sampling 0 setting and in the structural 0 setting, we might want to change the model. If we think that we're in something that looks more like a structural than a sampling. In other words, we got what first looked like, we got a 0, and we think maybe that even if we observe a ton of data, we'll never actually see something in that cell. Of course, this is also a big area of research, so let me just say a few things. So one thing is we can do is kind of delete the offending observations. And treat them as structural zeros. And there should be a good reason for this, of course, because saying it's a structural 0 is saying that not only did it not happen in my sample, but it will essentially never happen. And when we do that, when we force a cell to be 0, we have to adjust the degrees of freedom, because we've reduced the dimension of our model. We've reduced the number of parameters we need to describe it. Here's the adjustment. So remember, this is like a Poisson setup. So let me write this out and I'll explain what each of these terms are. Okay, so the usual thing is we take the number of cells, well, number of cells minus 1, but if I'm including the grand total, number of cells, and we subtract from that the number of parameters in the model. Right? So if I want to take some zeros that appear and turn them into structural zeros, what I should do, so this is kind of the number of cells we fit, or the number of parameters in the saturated model. This is the number of cells, this is the number of parameters in the model we want, or the model degrees of freedom. So that's the usual degrees of freedom for the test, is to subtract these. And then we subtract from the number of cells we fit the number of cells we want to zero out. So the number of cells we want to treat as structural zeros, and we have to subtract the number of parameters, and this is a little bit more subtle, number of parameters we can no longer estimate, which may not be exactly equal to this. Estimate because of the zeros. If you have it set up right in SAS and R, sometimes you can accomplish this by just deleting the observations that correspond to 0 cells. So if you've written it out not in terms of data point, like if you've written it not in terms of the data rows, where each observation has count 1, but in terms of the cells, and you have all the cells listed and one of those cell entries is 0, and you just don't put that in, you'll generally make this adjustment for you. Of course, the big picture is that if you want to make sure that your analysis is robust, given that you have so many choices, you should do some kind of sensitivity analysis. So sensitivity means essentially try all these things and see if they all give you the same answer, then you're probably okay. If they give you different answers, you should think about it a little bit. You can move or delete influential observations. Right, so if you have a table like this, for example, you could try just taking one from this and putting it here, taking one from this and putting it here, or taking one from this and putting it here, and see how much that changes your answer. If it doesn't change it much, then maybe it's probably okay. So if you take a small perturbation of your data, you take your data and you add some small number to it or subtract some small number vector to it, how does that change the inference? You can look at the influence diagnostics, so this leverage type of idea. And add different ad hoc numbers. So try adding a half, try adding 10 to the minus 10. Do your inferences change a lot, or do the inferences stay more or less the same? Okay. I also want to talk about the effect of the sparseness on goodness of fit statistics, but maybe I'll put that off to next time so I have a little bit of time to hand back your exams. So I have your exams.